This video is about related rates, and this is what happens when you have more than one quantity that is changing as time changes. So, for instance, if we do the first example, a rock is dropped into a lake, and circular ripples start to form as it spreads across the lake. You drop the pebble in, and it makes like a little circles that get bigger and bigger. And we're gonna model the shape of the ripples off of a circle. And so what's happening is, as the ripples spread out, the radius is changing. There's a one radius, and there's another one, and then there's another one. The radius is increasing as time goes on, and as well as the area of this circle, this area. Okay, so this is the situation, and so we could talk about the radius, but we also know that the radius is a function of time. So this is his rate of change, and this is what the actual measurement is. And then we could take a moment in time and say, what's the area of one of these circles? But also we realize that the area is changing with respect to time. So they're both functions of time. So circular ripples spread across the surface of the water, with the radius of each circle increasing at a rate of 3/2 feet per second. So the rate at which something moves is a derivative. So dr dt is equal to 3/2 or 1.5 feet per second. That's what they told us in the problem. Find the rate of change of the area. Okay, rate of change is another word for derivative of the area. So this is what we do not know. We need to figure this out. Formed by a ripple at the instant that the radius is 4 feet. So at what moment in time do we want to know the rate of change of the area? Well, we want to know this when the radius happens to be 4 feet. So what we need is a formula that ties both of these quantities together. And so here's one. The area of any circle is equal to pi r squared. And so this is something you learned a long time ago in math, hopefully, in a geometry class or somewhere. So what we do is we have this formula that is true, and we walk up to it and we take the derivative with respect to time on both sides of the equation. So when we take the derivative of a with respect to time, it turns out to be dA dt, derivative of area with respect to time. When we take the derivative of pi r squared, pi is a constant, he just hangs out. The derivative of r squared is going to be 2 comes in front times r times dr dt, because radius is a function of time. So the derivative, this is like tacking on the y prime. So now we plug in what we know. We're looking for this. So this is going to equal to pi times 2. The radius at this moment is 4 feet. The radius is changing at a rate of 1.5 feet per second. And then we can calculate all of this. And it turns out to be 12 pi feet squared per second, which is approximately equal to 37.7 feet squared per second. Feet squared is a unit of area, so this is the rate of change of the area with respect to time when the radius is 4 feet. All right, so that just kind of illustrates what related rates is. Let's do one with revenue. A company is increasing production of peanuts at the rate of 50 cases per day. So it's increasing the production of peanuts at the rate of 50 cases per day. That is dq dt. That is how much production is changing with respect to time. That's what dq dt is equal to. All cases that are produced can be sold. The initial demand function is given by P is equal to 50 minus Q over 200, where Q is the number of units produced and sold. P is the price. Find the rate of change of revenue. Find the rate of change of revenue. Okay, revenue. Find dr dt. That's what we have to find. With respect to time, in days, when the production is 200 units. When, at what moment in time? When Q is 200. Well, to start this problem, like in the last problem, we had to find a formula that relates everything together, and area of a circle was pi r squared, and so we had area and we had radius in there. Now we need something that will relate, we need revenue. So revenue is always equal to the amount you're producing times the price. So the amount we're producing is Q, and the price is this, 50 minus Q over 200. So now we have everything in terms of Q. So if I clean that up, over here, revenue is equal to 50Q minus Q times Q is Q squared over 200. So we come to this equation and we take the derivative with respect to time on both sides. So the derivative of the revenue with respect to time is dr dt, and that's what we are trying to figure out at when Q is 200. So that's equal to 50. The derivative of Q is 50Q would just be 50, but Q is a function of time, so we tack on the dq dt, kind of like the y prime for implicit. Now we take the derivative of negative Q squared over 200, so the 2 will come in front, so we'll have negative 2 over 100 or negative 1 over 100 times Q times dq dt, which is like the little y prime. We plug all of our numbers in because we want to know when Q is 200. This is going to be 50 times dq dt is 50 cases per day minus 1 over 100 times 200 is the amount of production times dq dt 50 cases per day. And when we multiply all that together, we get 2,400. So this is how much the revenue is changing per unit. So at a production level of 200, the revenue is increasing at $2,400 per unit. Okay, so let's do a few of these. Let's do 13. A cost of handcrafted wine racks has determined that the cost to produce, a manufacturer of handcrafted wine racks has determined that the cost to produce X units per month is given by C is equal to 0.2 X squared plus 10,000. How fast is the cost per month changing when production is changing at a rate of 12 units per month and production level is 80? All right, so what did they tell us? They gave us a formula for the cost, which is 0.2 X squared plus 10,000. Okay. They want to know how fast is cost per month changing. What is dc dt? This is what we have to find out. When production is changing at the rate of 12 units per month. At what moment in time? Well, this time they didn't tell us when X is up. They said when dx dt, when the rate of change of production is 12 per month. That's what they told us. And the production level is 80 units. Oh, they did also tell us that. And X is 80. All right. So we walk up to our formula that involves all of the variables we're interested in, and we take the derivative of it with respect to time on both sides. So we find that dc dt is equal to 0.2 x squared. His derivative, the 2 comes in front, it becomes 0.4x, but x is a function of time, dx dt. The derivative of 10,000 is 0. So what we need to do is we need to plug in 12 for dx dt, and we need to plug in 80 for x, and when we do that, we find that we get 384 per month. So what we can say is that the cost is increasing at a rate of $384 per month when they are producing 80 units and the production level is 12 per month is the rate of change of that. All right, let's look at 14, cost and revenue. A manufacturer has found that the cost C and the revenue R in dollars in 1 month are related by this equation. So cost and revenue are related here. Find the rate of change of revenue with respect to time. That means find dr dt. We don't know what that is. When cost is changing by this much per month, when dc dt is $15 per month. And the monthly revenue in R is $2,500. That's what they told us. We walk up to this equation and we take the derivative with respect to time on both sides of this guy. The derivative with respect to time of cost is dc dt. The derivative with respect to time of r squared over, this is a constant, 1 over 450,000 is a constant. So it's, the 2 is going to come in front. So 2 over 450,000 times r times dr dt. Plus derivative of 12,000 is 0. So now we just come in here, because we're looking for dr dt, we can substitute 15 here. 2 over 450,000. The revenue is 2,500 times dr dt. To solve for dr dt, we will take 15 and divide by this. And when you do that, you get that dr dt is $135 per day. The revenue is increasing by at a rate of $135 per day with these set conditions. Okay, let's go down here and do 25. Sociologists have found that crime rates are influenced by temperature. In a Midwestern town of 100,000 people, the crime rate has been approximated as, I'm sorry about my dogs, C is equal to 1/10 times T minus 60 squared plus 100, where C is the number of crimes per month and T is the average monthly temperature in degrees Fahrenheit. The average temperature for May was 76 degrees, and by the end of May, the temperature was rising at 8 degrees per month. Just a second. Okay, so how fast is the crime rate rising at the end of May? So what is dc dt? This is what we have to find. What did they tell us? C is the number of crimes per month. T is the average monthly temperature in degrees Fahrenheit. The average temperature was 76 degrees, and by the end of May, the temperature was rising. dt temperature is changing with time at 8 degrees per month. Okay, and they're saying the average temperature for May was 76 degrees. All right, now, let's see. What we want to do is walk up to this and take the derivative with respect to time of both sides of this. So the derivative with respect to time of the cost is, crime rate is dc dt. And this, we can use chain rule. Derivative with respect to time, the 2 can go in front. So dc dt, this is a C, that's a C, is equal to 1/10 hangs out. The 2 comes in front, so it becomes 2 over 10 times T minus 60 to the first power times the derivative of the inside function, which is just dt. So we can plug in all our numbers. We will get 2 over 10 times 76 minus 60 times dt, which is 8. And this comes out to 25.6 crimes per month. So that is the rate of change of the crimes at the end of the month of May. All right, the last example we're going to do, and I posted the key to this worksheet so you can find all this. This one's kind of straightforward, 15, when you look at the key posted in Canvas. But right here, let's just do 21, the brain mass. The brain mass of a fetus can be estimated using the total mass of the baby by this. So B is the total mass of the baby. And, no, I'm sorry. I got that wrong already. The brain mass, the B stands for brain mass. M is the total mass of the baby. Okay. Can be estimated by this, where M is the mass of the fetus in grams and B is the brain mass in grams. Suppose that the brain mass of a 25-gram fetus is changing at a rate of 0.25 grams per day. Use this to estimate the rate of change of the total mass of the fetus. So they want us to find the total mass. Okay. And what they told us was the brain mass is 25 grams. So B is, no, of a 25 gram fetus, sorry. The brain mass of a 25 gram fetus. So the total mass is 25 grams. And the brain, okay. I'm so sorry about that. Okay, so here we go. Brain mass is given by this formula. M is the total mass of the baby. Under these conditions, they want us to find the rate of change of the total mass of the baby for a 25 gram fetus. And the brain mass is changing, or dB dt is changing at a rate of 25 grams per day. All right, here we go. Walk up to this equation, take the derivative with respect to time of both sides. So dB dt is equal to 0.22 m to the 0.87. We need to take this guy's derivative. So you can think of m as x. So this is just a power rule. So it's going to be the power comes in front times 0.87. M is going to get raised to the 0.87 minus 1, which is negative 0.13 times the derivative of the mass with respect to time. Okay, this is what we need to solve for, but we have values for everything else. So we're going to say 0.25 is equal to 0.22 times 0.87 times m, which is 25, raised to the negative 0.13 dm dt. So we're going to take 0.25 and we're going to divide it by all of this to solve for this. And when we do that, we find that the rate of change of the total mass is 1.98 grams per day. So for a 25 gram fetus, when their brain is growing at a rate of 0.25 grams per day, the total mass is increasing at a rate of 1.98 grams per day. All right, that is related rates.